So your first type is if you could split your integral, your fraction up over a common denominator. This is a bit, I suppose, like doing really simplistic polynomial division. So there's two ways that you could do this. First thing is you could split that up over a common denominator because you're simply adding fractions. Or if you prefer, you could take out a factor of x squared on the numerator, and you can see that you're going to have an x squared divided by an x squared, whichever one you choose to do, you are going to then end up where the straightforward integral, the sort of thing that you would have been able to have done apart from the ln of the integrating 3 over x. It's the sort of thing you could just about have done in year 12. So you're going to end up with that. So obviously you've got no limits, so don't forget your plus c. Right, second type, reverse chain rule. Now you can use reverse chain rule if the function in the bracket, and I've put bracket in inverted commas because it might be it's a square root, or it might be that it's written in a different way. If the function in the bracket is linear. So here's an example of an integral you can do using reverse chain rule, where you simply raise the power by 1, divide by that new power, and divide by the derivative of that bracket. So here I've raised the power by 1, I've divided by that new power of a 6. If I differentiate that linear bracket, I'm going to get 4, so I divide by 4. And again, this is straightforward checking. You could just check that by differentiating it. Right, type 3. This looks like it could be reverse chain rule, where you can raise the power by 1 and divide by the new power. But the problem is the function inside the bracket is not linear. E to the x is, it's a classic curve shape, so you cannot use reverse chain rule here. And the only thing that you can possibly do is expand those brackets. So square it, just be careful, remember e to the x times e to the x is e to the x all squared, or e to the 2x using your laws of indices. And then you've got a straightforward integral where you divide by the derivative of your exponential power. And when you integrate exponentials, the powers stay the same. Right, type 4. Okay, you do have some formulae given to you on your formula booklet at the front of the exam paper. And so what you've got to do is be able to recognize the different types. Now, I can't split this up over a common denominator. My denominator doesn't factorize. I can't do polynomial division because the order of the numerator is less than the order of the denominator. So I'm going to see what happens if I differentiate that denominator. If I differentiate the denominator, I'm going to get 3x squared plus 2x, right? It's perfect. You are going to be using that formula that you've been given. So it's straightforward. If you integrate that, you are going to get a natural log of your denominator. That was a straightforward one. Occasionally you're going to have to rewrite it. Try and ignore that blob that I've got there above the 30x on the numerator. So again, I'm looking at this. I can't split it up over a common denominator, and I can't do polynomial division. However, if I differentiate that denominator, I'm going to get 6x plus 2, and I notice that that is double my numerator. So I rewrite my numerator by doubling it, because I can't just do that. I've got to knock that out by dividing by 2, and then it's in a straightforward form where I can use that law that we have from our formula sheet. So I'm going to end up with that as my answer. Right, type 5. Type 5. Now this is where we've got a product, and there's different ways that we can integrate a product. What you notice here is that there is a connection between the two functions. If I differentiate x squared plus 3, I will get 2x. So I'm going to use this formula here, which we know as Miss Awan's formula. That is given to you in the formula booklet. You can see that your f of x is x squared plus 3, and you know that the derivative of that function, that inner function, is 2x. So you can straightforwardly apply your Mr. Wan's formula. If you're feeling a bit unsure, you could then check that by differentiating, and which I've done there. Occasionally, you have to think a little bit more. Again, you are going to be able to use your Mr. Wan's formula here, even though it's not written as a product at the moment. You can rewrite it. Right, I'm looking at that, can't think of what on earth I'm going to do. Can't split it up over a common denominator. The derivative of the denominator is certainly not the numerator, so I'm going to attempt to rewrite it as a product. And I know that if I rewrite that as a product, my inner function is going to be x squared plus 2, and the derivative of that is 2x. So, rewriting it as a product, all I've done is I've adjusted it slightly so that that x has become a 2x, and of course to do that I've had to divide by 2 at the same time. So rewriting it as a product, I'm then going to use my Mr. Wan's formula, and I end up with a neatened version of my solution that looks like that. Right, if again, staying with quotients, type 6, if my denominator has been factorised or factorises, so here, don't know what to do, can't split it up, can't do any, the derivative of the denominator is certainly not the numerator, but I can factorise it. So I can factorise that denominator, and if I can factorise the denominator, I can split it up using partial fractions. So you've done a lot of practice with partial fractions. So again, I've sorted out my A and B over my linear factors, and then I am able to integrate it. So I've got, that's just a classic case of integration using ln, and I've summarised it at the end a bit, maybe more neatly, using laws of logs. Okay, sometimes it's going to be ready factorised for you, and you can see here that you do have a repeated factor, so I've just done a type like this where you can clearly see your repeated factor. Okay, and then straightforward partial fractions. Maybe I should have put a little bracket on that x plus 3. And then comparing my coefficients. So I've done my classic partial fractions solution by substituting values of x in, and then I'm ready to integrate. Don't get caught up in the whole ln thing, because you've got your middle integral there, which is straightforward chain rule. So obviously you've got your ln, then again you raise your power by 1, which is going to go from -2 to -1, divide by your new power. So you're going to end up with that as your solution. I've seen a couple of these in differential equations. This seems quite common, that when you're solving a differential equation, you then go to and it asks you to integrate, and you are going to have to use partial fractions, and you would know that because you have you can't do anything else, but you can factorise the denominator. So this is an example of one that's been on the practice papers, where you would split that up, work out your A and B. Not very nice. So I've then simplified that, and it's been much more of a straightforward integration than at first you might think. So finishing off like this, you may recognise this question from one of the practice papers. And you've always got to be mindful of, can you do polynomial division? Can you do polynomial division? Well, you can do polynomial division if the order of the numerator, and by order I mean the highest power, is greater than or equal to the order of the denominator. So here, again, I can't split it up over a common denominator, but the order of the numerator is 2 and the order of the denominator is 1, so I'm going to do some polynomial division. And so I do my polynomial division and then rewrite my integral, and this could then, you could then use any of the other techniques that we've looked at already in this video. So here, after my polynomial division, I can now integrate that in a quite straightforward fashion. And then I've just done one other little type here. Again, that order, the order of the numerator is the same as the order of the denominator, so you can do polynomial division. You rewrite your integral, and it's going to be written in that form. Okay, if there are products that have no connection, so here I've got x times the sine of x. There's no connection between those functions. One's not the derivative of the other. You can't make any connection. It has to be integration by parts. And remember, it can be written, that's given to you in your formula sheet like that. You can use the summarized version. And remember, we have Mrs. Reed's late about making choices for you. You know, if you are going to select a function for you, ln first. If you don't have an ln, it's an algebraic term. Trig, exponentials, you would rather never make those u, and they are obviously third and fourth in your choices. So here, these would be your choices for u and dv dx, and then you would work out what du dx is and what v is. I've used u dash to summarize du dx. Rewrite it by putting in your formula and then actually do your integration. So you can see I'm just doing a little bit of simple trig integration. However, you will be expected, sometimes it could ask you to integrate by parts twice. So here again, no link between those two functions. You would set up your integration by parts, just being super careful. Substitute it into your formula. However, you are then left with an integral of x e to the 3x. So I've taken out some common factors. You then step outside the question. You consider your x e to the 3x. Okay, and you perform integration by parts again. So it isn't super hard, but you've got to be really organized, especially if there's any kind of negatives that you're going to have to multiply by. So again, you perform integration by parts twice. You then substitute that back into what you'd left off. Now, I'd got a factor of minus 2/3 outside, so I'm then going to have to expand my bracket.